The next concept we need to deal with in topic 4.1 on special relativity is about momentum. Before we get into momentum though, I just want to identify this idea of rest mass. Now you'll recall from what we did with time dilation and length contraction, we had the proper time interval and the proper length. So rest mass is a similar sort of idea, relating obviously to mass. I'm just going to write down what the definition is here as given in the syllabus. You'll note that we use a subscript naught the same way that we do for proper time interval and proper length. The definition here is fairly similar to the definitions for those two quantities of proper length and proper time interval. It's the mass of an object when measured in the same frame of reference as the observer. So as with those other two quantities, it really just means that there is no relative motion between the object and the observer. So it's in the frame of reference of the observer. Note that we didn't have a term for relativistic mass in that dot point in the syllabus, so we'll talk about that a bit later in this video, just to draw your attention to that now. But what we're going to consider here is that on Earth, when we're talking about measuring mass, we typically have to use gravity in order to measure what that mass is. And what I mean by that is that in order to measure mass, you might stand on scales, or you might use a mass balance in order to determine what the mass of the object is. In doing so, you're actually using the weight of the object, so what the force due to gravity is for that object, and then converting it back to a mass. So if we then take that across to consider what happens for an object that's moving, it's a little bit difficult. We can't really have a moving object sitting on a set of scales to measure what its mass is. And so we need to use a different way of determining an object's mass if it's in motion. And we already have covered a concept that allows us to determine an object's mass. And I mentioned at the start of this video that we're looking at momentum, and it's that particular property that we're going to tie into. So another method that we can use involves its momentum. So if you recall the definition for momentum, it's a little bit of an unusual one compared to most quantities that we deal with. And we define momentum simply as the product of mass and velocity. Now, because we're dealing with mass, we're going to be a little bit more specific here, and not just talk about mass as the term that we usually refer to, and what we take for granted and how we always deal with it. Given that we're dealing with relativity, we're going to refer specifically to the rest mass. So the equation would usually be P is equal to mv. We're going to add the subscript naught there to indicate that momentum is the rest mass times velocity. And it's important to note here that that deals with Newtonian physics, not necessarily relativistic physics. So there's a little adjustment that we need to make in order to start to look at relativistic momentum. Before we do that, let's just first of all identify that momentum is always conserved in all collisions. That means if we know the velocities of an object before and after a collision, we can then actually calculate its mass based on the way that it's interacted with other objects in that collision. So that's really where momentum starts to become useful, when we can look at what happens as it's transferred in collisions. And it will even be conserved in collisions that are involving relativistic speeds. And that means that when we've got objects that are moving at very fast speeds, so things like protons in the Large Hadron Collider, they would undergo collisions where we'd need to consider their relativistic momentum. And in order to do that, we actually need to adjust the equation for relativistic momentum in the following way, and you'll notice that this adjustment is similar to some that you've already seen. If you go looking up other sources, you'll see that this is sort of the end point. I'm not going to bother putting in the extra little step that will often get mentioned, mainly because in the syllabus all you really need to be able to identify is that the equation for relativistic momentum is m0 v, so you can see that still looks like our Newtonian physics representation, but now we need to divide that by the term that we've seen a few times already, being 1 minus v squared on c squared. So that's the equation for relativistic momentum. So v being the relative velocity between the two objects, or between the object and the observer, and m0 being the rest mass. Now the definition for relativistic momentum that you need to be able to use, and again from the syllabus, is as follows, and not surprisingly it's not too dissimilar to other relativistic quantities that we've defined, is the momentum of an object when it's measured in the frame of reference in which that object is in motion. So anytime we see that idea of a relativistic quantity, we're always going to see that it's relating to an object that is in motion, and relativistic momentum is no different. So there's the key points to identify. I just want to touch back on something that I mentioned earlier in terms of mass and why we don't refer to a relativistic mass. And I'm not actually going to write any notes here because I don't want to confuse you and jot something down that you don't actually need to recall, but I want to make you aware of it at the same time. If you look at that equation, PV is equal to m0 v over the square root term, if you were to divide both sides by v, you might then sort of think that on the left hand side, PV divided by v would give us m. So then we'd have m is equal to m0 over that square root. You will actually see that equation in a number of sources. You could consider there that m is the relativistic mass, and you'll note that that equation would be in the same form as time dilation. That would suggest that m is always greater than m0. So one way that that can be interpreted is that relativistic mass increases depending on the relative velocity of the object and the observer. Now, while that does seem to make sense in an equation, Einstein himself actually warned against that interpretation, as there's no clear definition for why that occurs. So there's no easy way to identify why it is that the mass of an object would increase. We can have a look at time and length and identify why those quantities seem to change when moving at relativistic speeds. But as I said, Einstein identified that there's no clear definition that can be given to explain why the mass would increase. And so he instead preferred the consideration of momentum, as we've already just discussed. So like I said, if you do happen to look up other sources and you notice that equation, you don't need to worry about it. We're not going to consider the idea of mass increasing. We're instead going to focus on momentum being the property that we can actually calculate and explain in a way that somewhat makes sense. One last thing I want to note about this equation is the way that we can again tie it back into the Newtonian physics version of momentum, and that's by identifying that if we consider the velocities being extremely slow compared to the speed of light, so v being much, much less than c, then v squared over c squared is going to approach 0. And if we follow that through, 1 minus v squared on c squared is going to be close enough to 1. So we end up then with PV being equal to m0 v. So there's the Newtonian physics version. So you can see at very slow velocities, we still get that same calculation for momentum. Finally, let's just have a look at a quick example of a calculation that uses relativistic momentum. I mentioned earlier about protons in the Large Hadron Collider, so we'll use that as a context that makes some sort of sense and is actually relevant, rather than some of the somewhat unrealistic scenarios that we've been dealing with regarding Alice and Bob. So if we consider the relativistic momentum of a proton, and now you could look up in the data booklet that the proton has a mass of 1.6726. I've rounded that off to 4 decimal places there, so it's it actually has a bit more detail in that measurement in the data booklet, but we'll just use that value here. And imagine that it's moving at 0.999 times the speed of light. Now if you look up data about the Large Hadron Collider, you'll see that they can move even faster than this value here, but we'll just deal with that for this particular example. So to calculate the relativistic momentum, all we need to do is just substitute into that equation. Note that I'm going to write MP here because we're now dealing with the rest mass of a proton, and still divided by 1 minus v squared on c squared. So a couple of little things about this solution that we need to be aware of here as well. The first is that when you look at the velocity in the numerator, we need to consider that it's a fraction of the speed of light. So we can't just deal with 0.999 here. We actually have to multiply that by the speed of light, which is 3 by 10 to the 8 in the data booklet. Whereas in the denominator, we can just use 1 minus 0.999 c as the velocity, and that's all squared, divided by c squared. So you can see that we're going to have a c squared term divided by c squared term, so we can cancel those both out, and it makes the calculation just a little bit easier. So it's 1.6726 by 10 to the negative 27, multiplied by all of that detail on the top still, and then divided by the square root of 1 minus 0.999 squared. And if you go through and calculate that value, you'll find that it's 1.12 by 10 to the negative 17, and the units for momentum kilogram meters per second. So you can see there, even at moving a very fast speed, the relativistic momentum of a proton is still quite small. So there's the details that we need to be aware of for relativistic momentum. We'll have a look at a few more problems in class to make sure that's well and truly under control. And in the next 2 videos, we'll finish up the last couple of concepts related to special relativity.